Okay, go ahead.
So today we have the pleasure to listen to Bruno Ziliotto, and the pleasure to announce him, my colleague and co-author. So Bruno is known for having worked on Markov decision process, stochastic games, differential equation, and more recently profit inequalities. And mainly for his counterexample and also for positive results sometimes. So we have the pleasure to hear him today speak about absorbing games with incomplete information and the Mertens conjecture. So you have 1 hour.
Okay, thanks for the invitation, and hi everyone, and thank you for being there. So I'm going to talk about zero-sum stochastic games with long duration, and more particularly about a result about existence of limit value in some specific class of stochastic games. And sorry, okay, yeah. So I will first do an extended introduction where I will just recall the framework of Mertens conjectures in an informal way, and what are the main known results, and what is my contribution to this literature. And then I will go to the formalism, and I will and then I will present the proof. Sorry, I'm just I'm trying to read. Okay, yeah. So yeah, I have this. Thank you. And then I will explain the proof and give some perspective. Okay, so what very generally, what is a stochastic game? So you have 2 players that are adversary, and so they play repeatedly a zero-sum game, and the zero-sum game may change from one stage to the other according to player's action. And so, really speaking, at each stage, player choose simultaneously some action, and action and current state, they will determine the stage payoff. So player 1 gets the state payoff while player 2 gets the opposite. And then a new state is drawn from some distribution that is a function of current state and action. So it's like a controlled Markov chain controlled by 2 players. So for instance, you can imagine that you are playing repeatedly the rock, scissors, paper game, and the rule is that if the rock hits scissors, then the scissor is broken, and you cannot use in the remaining stages, or maybe the scissor is broken with probability 1/2, and so on and so forth. Or maybe if you win the 10 times in a row, your opponent is really disappointed and he just leaves the game. Or there are many ways you can see this state evolving. And so far, I didn't tell anything about information. And of course, this is a general framework, but then you can be more specific, and you can assume, for instance, that maybe players know the state, maybe they know the action, or maybe they get signals about it. Maybe these signals are symmetric or asymmetric. You can also give assumptions on the dynamics of the state. So maybe once you leave the initial state, you get absorbed. So it's an absorbing game. Maybe on the contrary, your state will have an ergodic structure, so it will always come back to the same states. Maybe players play in turn, or maybe they play simultaneously, and so on and so forth. And you can also imagine topological assumption on states, on action, finite, compact, measurable. So this stochastic game framework can be split into like hundreds of different models. And in this talk, I will only talk about finite state space, finite action sets, and finite signal sets. So just a few sorry. Okay. So just a few important models. So of course, the seminal model of Shapley, which concerns stochastic games where state is observed and action is observed. So I will refer to them to it as standard. The Oman and Maschler model, in which the state never moves, but players don't know it, and they get just one private signal at the outset of the game. And then there were many other models, and this led to a general formulation of stochastic games with signals, where basically everything is possible. So at each stage, you get a signal that may be private for each player, and you may not know action, you may know the state, and it kind of encompasses all the previous models. And this were this on this model that the Mertens conjecture were stated. So don't hesitate to stop me if you have any question. So I give one slide just to explain why or to recall why zero-sum game is not just about solving elegant math problems. It's also prominent in game theory because it's first a good benchmark for non-zero-sum games. So the zero-sum case. So if you want to develop a new theory, it's convenient to first test it on zero-sum case because there is a uniqueness of existence of Nash equilibrium and things are more simple. It's also a well-known tool to build cooperation and punishment equilibrium in non-zero-sum games. So like you agree to play something that is good for everyone. I think if someone deviates, you punish them in the spirit of fault theorem. And also, there are many recent developments about optimization in adversarial environment where you have one decision maker that has to take decisions in an environment that he does not know, and he does not even have a Bayesian prior about the components of the environment. And then he can consider that actually there is an adversarial nature that chooses the environment, and that is playing against this nature, and then it can be modeled as a zero-sum game. And you also have concrete applications so for security games involving player one that wants to defend a facility and player two that wants to invade it or wants to steal something. And so there are also direct situations where that you can model as zero-sum games. So this was for the justification of importance of a zero-sum game. And I will introduce the main objects of this talk. So you are in a stochastic game. There are many stages. How do you aggregate the payoff? So a classical way is to consider that the game duration is n, and you take as a payoff the average expected payoff over the n stages. And you can call the value of this game Vn. Or maybe players have a preference for present versus future. So there is a discount factor, lambda, and you can define a payoff as a discounted sum. So game is infinite, but there is a discount. And then the value of this game is V lambda. So then, of course, there are many situations that have a very long duration. So if you want to study zero-sum games with long duration, basically it corresponds to n being very large or lambda being very small. And you want and you would like to give a solution to games with long duration. So what could be a good candidate? Well, you take this value of the n stage game and you make n goes to infinity. And you say, well, if players are rational, as the game is very long, then player one should get the limit of Vn and player two should get the opposite. And you can say the same thing with the discounted values. Now, of course, for this, to say that, you need that both these objects converge. And in addition, you would like that the limit coincide. You would like that your modelization does not depend on the fact that payoffs are discounted or not. And another question that people have investigated is, okay, so maybe Vn converges and V lambda converges, but still strategies that are optimal here and here may depend heavily on the duration of the game and on the discount factor. But maybe players don't know actually what is exactly their discount factor and what is exactly the duration of the game. So you would have to have a robust strategy in which players perform well, even if they don't know the exact duration of the game or the exact discount factor. And so this question is what is written there. So can a player guarantee uniformly in time some payoff, and which payoff? What is the maximum that he can guarantee? So without knowing the duration of the game, this is what uniform means. So the game theoretic motivation is to understand long games where players are patient. But this type of question is also connected to important problems in other parts of mathematics. So, for instance, if you take a continuous analog of these questions, you can show that sometimes these values that satisfies partial differential equations that are called Hamilton-Jacobi equations. And these PDEs are studied independently in mathematical physics. And there are papers where basically people prove existence of solutions of these PDEs using games. And also other papers where people studies the limit behavior of this Hamilton-Jacobi equation using the game theoretic interpretation. So this problem is interesting to understand long games, but it has also other application in other parts of mathematics. So let me now go to the formulation of the Mertens conductor. So Mertens conjecture some 30-40 years ago that both V lambda and Vn should converge to the same limit. So in some sense, the answer to this three questions are positive. And secondly, that in terms of uniform guarantee, when player 1 is more informed than player 2, then player 1 can guarantee uniformly in time the limit value. And this conjecture were actually motivated many works in the field, and I won't be able to quote all the work that has been done on the topic, but let me just say that it's the two seminal models that I talked briefly about in the previous slides, so namely standard stochastic games and repeated games with incomplete information on both sides. So recall that it means that here state and action are perfectly observed, and here the state does not move, but players don't know what is the state. Here the Mertens conjecture were proved to hold. And they were also disproved in general, so by stochastic games with public signals examples, so meaning that players don't know the state, they know the actions, and at each stage they get a signal, a public signal on the state. So it's harmful if you try to resurrect these results, and instead of assuming that players know the state, they get public signals on it. So the Mertens conjecture failed to hold, and actually both, like there is no limit value, and this is not true either. So of course, this is not the end of the story. There are still many models in which we don't know whether the Mertens conjectures hold, and so this is one of the motivation of my work today. And actually, in literature, there has been this idea, in several papers, that Mertens conjecture should hold when information is irreversible. So it's a bit difficult to define what irreversible means, but I will only give some examples. So for instance, if you are in a repeated games with incomplete information on both sides, the state does not move. So each thing that you learn about the states, you will be useful. So you progress along the game, you progressively learn the initial state. And so you cannot forget information. Otherwise, it's a problem. There is something irreversible, like mathematically, it's like a martingale thing. So the game advances. At each stage, you are more and more informed. And there are also, so in this type of model, we expect that the Mertens conjecture hold. And on the contrary, for instance, in the public stochastic games example, it could be that, okay, you remain at the initial state and you learn more and more about it. And then suddenly the initial state changes and the state is drawn randomly, uniformly. And then all the information that you have learned so far is completely useless. So typically this kind of game is not irreversible. And so this game does not have a limit value. So, of course, it's only heuristics. There is not so much theoretical stuff that to provide for this, but I think it's an idea that I really like. And I would like to maybe to add something to this idea, which is something that I've been thinking starting from my PhD. And I think it's probably the most natural and naive idea you can have to prove that a game has a limit value. I mean, naive meaning that if you have already read many books about it, like if you are in your second years of PhD, is like basically when you have a stochastic games with incomplete information with signals, you can transform it into a stochastic games where players know the state, but the state aggregates all the information available. So belief of player one about the state, belief of player two about the state, belief of player one about actions, belief of player one about the belief of player two, and so on and so forth. And this is what is called the universal belief space by Mertens, Sorin, and Zamir. And of course, this auxiliary belief space can be very complicated, but in many cases, it's rather simple. Like you don't climb the belief hierarchy too far. And so once you have written your stochastic game with signals into stochastic games where with perfect observation of the belief, basically you can try to discretize this belief space and show that this auxiliary stochastic game is close to a stochastic game with finite state space. And then you can apply the Boole-Kohlberg results and say that, okay, standard stochastic games have a value, so this game should have this value. And so the game on the belief space should also have a value. So it's a kind of a naive idea because it's just basically you have a result about a finite state space and you want to use it for infinite state space, so you just discretize. And I've never, unfortunately, managed to do that except recently. So this is the technique that I will use on absorbing games with incomplete information on both sides. And apart from the fact to add one more model where Methane's conjectures hold, it's also, I think, give some credit to this discretization argument, and maybe it will be possible to extend this technique to other types of model. So I will explain what is absorbing games with incomplete information on both sides in a few slides. But so this is basically the end of my introduction. As a questions so far. Okay, so let me now move to the formal model. So
hello everybody.
So basically, you have a state space omega. So action set I for player one and J for player two, and the type set K for player one and L for player two. And so it's an absorbing game, meaning that there is only one non-absorbing state. And if you are in, if you leave the non-absorbing state, your game is essentially over, meaning that once you leave it, the payoff will be the same forever, and whatever you do, and the state will never move again. So formally, it means that so when you look at the transition of your stochastic game, so which maps pair of actions state to a distribution over the state, it means that whenever omega is absorbing, then the probability that from omega you go to omega is 1.
But you just have to double click to open the PDF file.
Sorry.
Yeah,
okay. So the payout function is also does not depend on action. So once you are in an absorbing state, so basically the only relevant state is the non-absorbing state. And you can see that your payout function depends on your types, on which state you are. So it can still depend on which absorbing state you end up in, and of course on actions. And we assume that all these states are finite. Are there questions on the model? So it's basically an absorbing big game where where the payoff depends on two parameters, and player one knows the first parameter, and player two knows the second parameter.
And you assume that the actions are observable.
Yes. Yeah, actually, I will describe it I will describe the proceeding of the game in the next slide. So nature will draw player one's type K according to P, player two's type L according to Q. So player one knows his type and player two knows his type, but they don't know types of the other player. They still know P and Q, both. And then at each stage, player one chooses some IM, player two some action JM. And this is determined together with the types and the state, the stage payoff. So it's player one's payoff and player two gets the opposite.
Could you please make it full screen? Yeah, sure.
And nature draws the omega m plus 1 according to the probability distribution Again, it's a control Markov chain, so it depends on the current state and the pair of actions that have just been played. And the player knows the state and they know the actions. So the only incomplete information is about the types. Now, a strategy maps available information into mixed actions. So at stage M, player 1 knows his type, and he knows also all the previous stages, and all the previous states and all the previous actions. And same thing for player 2. So then they at each stage, strategy determines what players do in each situation. And the set of strategy of player 1 is denoted by sigma, and the set of strategy of player 2 is denoted by t. So it's just the usual way to define strategies. And again, I insist, so player knows the state, they know past actions, and they know their type. And so the end stage repeated game is just the game where your payoff is the expectation of the Caesar mean of your payoff. So determined by strategy of player 1, strategy of player 2, initial P, initial Q, and initial state. And the value is denoted by Vn of PQ omega. And you have also the discounted game where the value is the discounted expected mean of the payoff. And the value is denoted by V lambda. And again, it depends on the distribution of types and on the state. And just so just for a quick review of literature, so I say that I wouldn't be able to provide all papers about Mertens conjectures in stochastic games, but if you restrict to absorbing game with incomplete information on both sides, you can do some kind of exhaustive list. So we knew that Mertens conjecture hold in when basically there are only one type for each player, so it's standard absorbing game. So basically the type is irrelevant. Repeated games with complete information on both sides, I already talked about it. There is also a variation of the big match with incomplete information that has been extensively studied by Sorin. And there is also in the one side case, Rosenberg that proved existence of a limit value. Sorry, actually, I made a mistake here. It's only existence of limit values that was proved. And also Lee generalized the result of Sorin to some more general class of big match. So just to be sure, one side means that player 1 is fully informed. So it means formally that player 2 set of types is a singleton. So player 2's type doesn't affect the game. So player 1 is fully informed and player 2 does not know the type. Okay, so here is the result. So if you take an absorbing game with incomplete information of both sides, so Mertens conjecture hold, meaning that V lambda and Vn converge to the same limit. And when L is a singleton, incomplete information on one side, so for each epsilon, player 1 has a strategy that guarantees almost the value in any game up to epsilon, provided that N is sufficiently large. So this result was actually also new. And so the proof is a bit long, so I will only be able to sketch the proof that V lambda converges. Actually, we know that if V lambda converges, Vn converges. So this at least do the trick for this, but I won't have the time to talk about this part. Is there any question before I go to the proof?
Bruno.
Yeah.
I have a question regarding what happens when L is not a singleton. Then there is not necessarily such a strategy, or you do not know whether it exists.
Mertens Zamir, you know that it doesn't exist.
I think that exists, otherwise I would, no, I think yeah, it doesn't exist.
Okay, thanks.
Okay, the approach, so so as I said, the first thing is to write an equivalent stochastic game played on the belief space. So the state space is basically player 2's belief about player 1's type, player 1's belief about player 2's type, and the state. And we assume that this is a new state variable. I will describe in one slide what is gamma E, but first I just present a rough sketch. And the action sets will be delta of I to the power k, meaning that player 1 can choose his mixed action according to his type, because he knows it, and same thing for player 2. Then prove that V lambda converges in gamma E. And to this M, use a discretization argument. So you discretize the type beliefs to obtain some stochastic game with finite state space and a compact action sets. Now, this type of stochastic games may not have a limit value, but if it's regular enough, it has by work by Bolt, Gobert, and Visual, so about definable stochastic games. So limit value in the approximated stochastic game gamma F exists. And then the last thing and the most difficult is to prove that your approximation is correct. So meaning that the discontinued values of gamma E and gamma F are very, very close. So this is a roadmap of the proof. So let me start with gamma E. So these are classical definitions. So you have given a belief P and some mixed action of player 1. So this X bar P of I is like the average action. It's the probability that that player 1 plays I if he uses X as a strategy. So this is like probability of playing I, given that state is type is K. So this is like the general probability of playing I if you sum, and this is just the posterior belief given that the realized action was I and the strategy was X. So it's just a bias rule. Just posterior belief. Oh, sorry, I'm still not so used on my tablet. Yeah. Okay, so the text that I've just written will just disappear. So, but don't worry, it's normal. So basically, then gamma E is just the game with this state space, so this product. So this I already said, and the transition is the following. So imagine that you are in belief P, Q, the state is omega, player 1 plays X, player 2 plays Y. Then what is the probability that I is played? Well, it's just by definition X bar P of I. Action J is played is this probability. So when I and J are played, basically the probability that you jump to omega prime is by definition this. And in this case, your next belief is just the posterior belief. So this is just transition given by Bayes' rule and the transition of your stochastic game. Now the payout function is just the expected expectation of the payout function. So it's you sum over all the possible types. Given the types, the probability that player 1 plays I is this, that player 2 plays J is this, and then your payoff is this. So it's just expectation. And in this new auxiliary stochastic game, the previous states and action are perfectly observed, and your states are belief, and state. And action are the mixed actions. Okay. So we call V lambda E the discounted value of gamma E, and there is classic results that is actually true in a much more general framework, but that says that the discounted value of the auxiliary game is the same as the original game. And so the goal is to prove that V lambda E converges. And so, so for this, I will first maybe do a small drawing to explain how I will approximate gamma E. So I will approximate gamma E by a game gamma F, which has a finite state space. So I will draw the. I will only consider because everything is kind of symmetric. If I do something for player 1, I can do it for player 2. So I will only look at the belief of on player 1's type. Okay, so imagine you have a simplex delta of k. So this is the delta of k. And I will triangulate it. So we're using a regular triangulation. And I will try it to be as regular as needed. So it's a triangulation that is basically with a small step size. So it's an alpha triangulation, meaning that the distance between 2 points is alpha or smaller than alpha. And then, okay, I have, let's call a PM, player 2's belief about player 1's type. So imagine that my belief is like PM at stage M. Basically, I want to define an auxiliary PM prime that lies in the vertices of my triangulation. So what could I do? I could just so a first idea would be just to project PM on the closest point of the triangulation. But if you do that, it won't. So basically, you would say, okay, this is PM. So I will say that PM prime is this point. But if you do that, you will make a alpha error at each stage. But alpha plus alpha plus alpha, even if alpha is small, it's a lot. So it typically this does not work. It's like it's not the same thing to say there is a alpha probability that a pandemic starts this year, or to say that there is 0 probability that a pandemic starts this year. Unfortunately, sorry for the stupid joke. So basically, we are not going to do that. So we are going to make something a bit more subtle. We will consider that we look at this point, PM, and we'll decompose PM as a convex combination of this point, and this point. So maybe this is P1, P2, and P3. And we will write it as A1 P1 plus A2 P2 plus A3 P3. And then what we do is we will basically draw. So we will draw PM prime at random, but the probability that PM prime is equal to pi is exactly the coefficient. So I just compute at each stage the weights of PM on each of the vertices, and I draw P1, P2, or P3 according to these weights. Is it clear?
This is clear, but now you have to do it somehow with a public lottery so that they know what is alpha 1, alpha 2. What is the next P1 if you want to make it with as a stochastic game?
I will define formally the stochastic game in one slide. Yeah. So basically, at the end, we will obtain a stochastic game gamma f on a p times q times omega, where this is like the triangulation of delta of k, and this is the one of delta of L. And I will now define it formally. The next slide. So I take some alpha and p some alpha triangulation of delta de k and q of delta of L. And so for each p in delta of k, I can say that it's a convex combination of some point of the subsamplex containing p in just a way. So this is just the same thing, but in the general case. And okay, I do this for player 1, but I can also do this for player 2, and I will use the same notation. So S. So basically, this is S for splitting of P and the splitting of Q. And basically yeah. Maybe okay. Maybe I forgot to write what is S, but basically. So it's exactly as I said. So basically, the probability that that you draw P will exactly be Ik of P. And so basically, you now have a stochastic game on a P times Q times omega. Okay, your action sets are the same as in the gamma E, delta of I to the power K and delta of J to the power L. And your transition rho f now is the following. It's so again, if you play X and Y, the probability of playing A and J is just given by the average, as in the previous model. Same thing for the state. But now, instead of jumping from P to the posterior belief, I go from P to the posterior belief, and then I split it. So this is this thing here is AK of is the corresponding AK of P prime. So it's a component of my posterior belief according to my subsubject. Is it clear now, Abraham, or
No.
No?
How do you make the splitting? You want to make it a public splitting, right? So that they know what is the next state.
What I mean, it's a stochastic game. I can say that the probability are this.
No, but you computed the posterior, and now I am doing the splitting. But the other player has to know what was the splitting I was doing in order to view it as
a new game. It's a new game. It's a different game.
Yeah.
So Abraham, you ask why is the value of this game similar to the value of the original game?
Yeah, so I think you are kind of anticipating. Here, I just defined a game gamma f. I just said, yeah, this is my game is okay when I so compared to the original game, the game is the following. So you have you have some p.
Okay, then, show for a minute. Show for the minute the next slide.
Okay, yeah.
X of y.
So player 1 plays X, player 2 plays Y. This produces a posterior belief, and then it is split according to the triangulation.
Okay.
Bruno, a collection of posterior beliefs, no? For every I and J, there's a different posterior belief.
So for every I and J, there is a distribution. So for every I and J, there is a belief of player 1 and belief of player 2, and then you draw it again and you split it.
Why don't you sum over I and J in your formula? Because you want the probability of falling in P prime or Q prime, it has to be the sum over I and J, no, maybe?
No, Bruno, look on the first term of the right-hand side. So that's a function of I and J's.
I think you want to, it's not X and Y, it's I and J, no?
I think it has to sum on I and J, that's it.
Or
Okay,
to take the expectation of that, or what?
Yeah, but the player observe I and J, so you can put I and J here, I think.
No. The probability
No, it's X, Y, I. You should add I and J moreover to this.
No, the probably there are two types, Bruno. First, you have the omega prime, should be omega prime in the left-hand side. Go from PQ omega to P prime Q prime omega prime. And then you should sum over I and J because different I and J can give you the same P prime Q prime.
Okay, sorry, I agree. So this is omega prime. Agree. And yeah, okay, you have to sum for AJ.
Okay.
Sorry for that. So it's like, okay, the interpretation is like if player 1 plays X and player 2 plays Y, then IJ is drawn with priority X bar of I and Y bar of J. And then this produces a posterior belief, and then the posterior belief is split. Sorry for this mess. And then the payoff for the payoff function, you just basically, basically your state space compared to gamma E is just restricted. So you just restrict your former payoff function to the vertices of your triangulation. Okay, so
sorry. Let us have another second looking on this equation.
Yeah.
So this is the Q prime. Yellow row is from the original game. And then you look at the probability. And then okay.
Okay, so this is a game with finite state space, compact action sets. Of course, this is not enough to say that the game has a limit value, because there has been an example by Vijral, but in this example, the transition function were not so regular, but here it's you only have you have only like posterior beliefs and multiplication or division, so it's a very regular game, and so you can show that this game indeed has a limit value just by applying some theorem in this paper. So the only thing that remains to prove is that the discounted value of gamma E and gamma F are close to each other. So formally, for each epsilon, there exists some alpha that for any triangulation that is smaller than alpha, for each discount factor, for each starting point, starting belief point, and omega, then the value in gamma E and the value in gamma F are close to each other. So what is important here is that the bond is uniform in lambda. So it's like for every discounted game, your approximation is good, and the UIR term does not depend on lambda. So So actually, I will only do one inequality because player 1 and player 2 play similar role. So I will only prove that V lambda F is larger than V lambda E plus minus some error term. And actually, there will be some issues when the belief dynamics is close to the frontier of the simplex. So that's why it will be needed some induction arguments on the cardinality of types and the cardinality of L. So basically, what we are going to do is that is to say, okay, if you are not close to the frontier of the simplex, everything is good. And if you are close, then this means that morally, my set of types has decreased, and then I can reuse the induction hypothesis. So this is what I wrote here. So the resist is true when P lies in the frontier of the simplex. Okay, so I think at this point I will make some drawing again, and I hope that this is maybe clearer. Okay. So what we are going to do is a coupling between between gamma E, between the history of gamma E and the histories of gamma F. So I will call like PM again the belief of player 2 about player 1's type. So in gamma E, and PM prime the same belief but in gamma F. And I will consider some strategy sigma E which is optimal for player 1 in gamma lambda E, and tau F that is optimal for player 2 in gamma lambda F. And basically, what is the goal here? The goal is to copy sigma E. So sigma E is a strategy for player 1 in gamma E that is good. So this is lambda everywhere. So sigma E is a good strategy for player 1 in the original game gamma E. And so I want to transform it into a good strategy of the game of player 1 in gamma F. And then I can deduce that V lambda F is greater than V lambda E. So, and the other term, of course, will be a function of alpha. And so let's do this on the so I think I don't have, I mean, I was expecting this, I don't have that many time. I hope that my drawing will already be condensing. So again, I make a triangulation of delta of K. And I will explain how somehow player 1 that is playing in gamma F can follow the player 1 that is playing in gamma E. So I assume that there are like 3 actions, A, B, C. And so so we are at stage M. Okay, and so at stage M, player 1 plays in gamma E some actions that I'll call X. So what happens then? Imagine that I don't know, like PM is like there, and PM prime is like there. Now, the fact that that player 1 plays X makes a splitting of PM. So, for instance, like there. This is like A, B, and C. This is a possible split next variables for player 1 in gamma E. And what as a player 1 in gamma F, I will do the following. I will try to mimic. So basically, the interpretation is that I'm player 1 in gamma F. My belief is PM prime because sorry, I made a mistake. It should so the belief in gamma F should be in
the simplex.
And the
Yes.
amount of the artists. Yes, sorry.
Yes.
So let's say, for example, it's there. This is like PM prime. So what I would do is that I would play in such a way that my splitting will be the translation of this splitting. So basically, it will have the following shape. If I play A, I will just parallelize this one, and same thing for if I play B or C. It will have something like this. Sorry, so this is A, B, and C. So basically, I will select X prime, such that if I such that for all I, if I make the difference between my posterior belief when I play X prime and I was selected, this will be equal to PM prime minus minus PM. This is prime and so basically at stage M, what is my error term? My error term is PM minus PM prime. And so when I play, my error term between this and this will be exactly the same. So this will be, for example, imagine that A is selected. So this is PM plus 1. And here this is this is PM prime hat X prime, knowing that A was played. Okay, did you get this thing? You can always split like that. Is it clear? Or...
Not yet, but
in the border, it's not possible. No?
What happens at the boundary? Yeah.
Yeah, sorry. So that's why, of course, in the border it's not possible, but that's why I'm making an induction. So when I'm close to the border, I can reuse the induction. But I agree, there may be a problem in the border.
And you want to small splitting and small splitting.
Additional splitting that we didn't take care of now.
Yeah, but I've not finished my drawing.
Yeah.
I agree.
Then it cannot be clear yet.
Okay, and then we can do some. We have some additional splitting like this. Because basically you resplit in the game. So actually, maybe your actual PM plus 1 prime is like that. But it's fine because at the end of the day, what will be the difference between PM plus 1 prime minus PM plus 1? it will be the same as the difference between PM prime and PM, plus some error term that is just white noise, basically, because it will be the difference between PM plus 1 prime minus this thing, so P prime M hat X prime, knowing that IM was selected, so action IM. But this has expectation 0. So basically, at each stage, you keep your in expectation, you keep the same error, but maybe you do an expectation 0 error. And the hope is that when you extend this formula, so you extend this formula, you get basically that the difference between PM prime and PM is the sum of variables that has expectation 0. And sometimes thanks to the law of large numbers, you can prove that such things are smaller. And this is essentially what. Okay, so I have 1 minute left. Anyway, did you understand this decomposition?
Where do you use absorbing game? Irreversibility.
No, for the dynamics, you don't use it actually.
No, you use it by the fact that probably, I would guess that you use it when you allow compact action sets. And because it's an absorbing game, so you could work just with until the absorptions, just with the posteriors on the K and L. And you know that after many splits, basically you're approaching the boundary. Is not that the case?
No, but the fact that you approach the boundary, there are two things. There are the dynamic on the state and the dynamics on the beliefs. When I say reaching the boundaries, I talk about beliefs. So maybe
from the state, you could have only one state change. Okay, so you cannot come back and forth and then back to another state.
Yes.
Yes, and then on the belief, you could switch to the fact that you could work with compact action sets because the number of splittings that you have on the beliefs is basically finite. Each time you have some jump of the belief.
Yeah. Okay,
so you approach the boundary.
I cannot really answer. I would like to finish in 1 minute and then we can do. Okay, anyway, what I just described, you can do it quite easily. You just write some formula. Okay. Basically, this is what I call the X prime. You can write down some formula. You can write down also, this is what I said about the fact that the difference between the error terms correspond to a term with expectation 0, whatever. I cannot do the formal couple coupling, but anyway, I would just like to explain where absorbing comes from. So basically, the whole goal of this approximation is to prove that that PM prime, so the belief in gamma F is close to the belief in gamma E. So you want to prove something like this, some results that the probability that is large is big O of epsilon. And as I said, you can write down a formula between PM prime and PM as a sum of terms that have expectation 0. And then you can apply some martingale inequality, okay, that I can detail. But the whole point is that at the end of the day, what you will obtain as a majoration of this is something that depends on the L1 variation of your belief PT. So at the end, you will obtain something like this is smaller than the grid times the L1 variation of the martingale of beliefs. But we don't know whether this L1 variation of belief is bounded or not, because if you have a martingale, you know that the L2 variation is bounded, but you don't know if the L1 variation is bounded. So basically, here there is. So actually, I did not manage to finish the proof, but the proof that I wanted to show you was only half of the proof, actually. So at the end, I still missing some, at the end, I will still missing some result like this. So that says that in an absorbing game with incomplete information on both sides, you can play epsilon optimally in such a way that the L1 variation of your belief is not too large. And for this thing, you need that your game is absorbing. If the game is not absorbing, I don't know how to do it. So I would just I just wanted to say where actually the absorbing assumption comes from. This is not something that I was planning to show because it's not so easy to do, but you can do that. Basically. So I'm sorry for having overlapped like this. So I will give up on perspective and maybe answer your question. Thank you.
Okay, thanks, Bruno.
Sorry, can you show the previous slide for 1 second?
Sorry?
The previous slide. No. The next one, when you write result, it remains to prove result admitted. What does it mean, result admitted?
No, it was admitted for the talk because I knew I wouldn't have the time to do it.
Omitted. But it means that's a result, yes?
No, I have the proof. I can send it to you. I'm not...
No, I guess you meant omitted, not admitted.
Ah, sorry. Yeah, admitted for the talk.
Yes, okay.
So Bruno, so it is true that if you fix lambda, then the approximation you did works. In fact, so it just if you want when you want to have lambda goes to 0, then you need this result. This is where you use absorbing game somehow.
Sorry? No.
If you fix lambda,
I want absorbing because I want to prove this. Yeah, I want to prove that my approximation is good. So I want to prove that my approximation is good. For this, I use Dove's martingale inequality, which gives me a bound on this thing in function of the L1 variation of my martingale. But this L1 variation, I don't know whether it's bounded or not. I mean, it could be very high. It could be much larger than alpha. I don't know. Because there is nothing that says that L1 variation of martingales. I mean, if you think about like discretization of Brownian motions, the L1 variation is of course very high. So, but that's why you need to construct specific type of strategy that will allow you to this to hold. But this I was only able to do it for absorbing games.
And what kind of how do you do your strategy?
This thing?
Just a quick idea of the strategy.
So okay. Maybe I can answer other questions and come back to this because it could be a bit long. So. Is there any other questions?
So Bruno, does your approach extend apply to recursive games?
I really don't know actually. I mean, I finished this very recently, and I didn't have the time to investigate other models. But actually, yeah, I would love to see whether you can apply to other models.
Let me give an answer to, I think, an early question of Sylvan. It was, how is the beach in Tel Aviv or in Israel? So this picture is from this morning.
What? Which picture?
The background on my...
Ah, well, okay.
Very clear water, very nice sea. You're all invited.
Cool.
As soon as there is no lockdown, we come.
You could teach. You are teaching in Zoom. You could teach it from here. Yes, no problem.
That's true. That's true. Bruno, my question.
Okay, so thank you everyone for attending the talk. I will answer, of course, Reda's question, but I also apologize if I was a bit fuzzy sometimes. It was a very recent result and I was very excited about it. So I really wanted to present it, but maybe it was a bit early to present it. So anyway, okay, so where is this? So
I see I'm muted. I say it very good that you presented it. Yes.
Okay, thanks. So basically, the idea is to define the notion of concise action. It means that for all, so epsilon concise, so there is some epsilon, and concise action, epsilon concise action X means that sorry, that's not what I meant. Okay. Sorry, so epsilon revealing action, sorry, means that you reveal, but significantly, like your belief jumps from epsilon. So typically, it will mean that there exists some k x I knowing k is larger than 1 plus epsilon x of like for instance the average action. So I is an epsilon revealing action with respect to x and p. If this is true, so this means that there is the component on k will typically jumps a lot. So like you reveal a lot, and so given x in delta of a to the power k, you will define some new x prime. The intuition of x prime is like okay, there is no point in revealing just a little bit in a game. Like if you just reveal a very small fraction, you could just play the average action, and it will be as good. So basically, the idea would be to transform x in just a way that the action where you reveal a lot, you keep them with the same probability, and the other one you kind of average them. So you define the new mixed action where this will be x bar p of non-revealing epsilon action, knowing k. So as I said, I distinguish between revealing action and actions that are not revealing. So all the revealing action, I keep them like this. The other one, I try to average them in some way. So I cannot, since all this might be different, I cannot compel the epsilon non-revealing action to be exactly non-revealing. So I do some average like this. And basically, what I claim is that so if you take sigma an optimal strategy in gamma lambda, and you define sigma prime such that sigma prime of H corresponds exactly to this prime thing applied to sigma H. So after every history, you do this this transformation. Then two things. First, sigma prime will be like I don't know, 10 epsilon optimal. Second thing, it will generate something that is that can be bounded without square. So it can generate the L1 martingale variation that is bounded by something depending only on epsilon. And this thing, it will be, I don't use absorbing, but for this I use absorbing basically. Neither this nor this is so easy to do. I mean, yeah, you have to do some proof. But basically, the whole idea is that basically your strategy either it makes significant jumps on the belief, but the point is that when you make significant jumps, there is no so much difference between putting a square here or not putting a square. Like, okay, if you like 0.25 to the square is not so so far from 0.25. But if you, of course, if you have something very small and you want to compare it to its square, it's another story. So the whole point is somehow to stop revealing small and only reveal when it's needed. It's not as simple as that because you cannot just you cannot create a strategy that it's really like this. Like either you make huge jumps or you don't make at all. But somehow you can do something in between that that works. I mean, I know it's not a proof, but you need a few pages for each of these things. And I'm just giving the rough idea. I can send you the notes if you want.
Okay, I have a question which is less technical.
Yeah.
So we know the
who are you?
What?
Who are you?
I don't know.
Hello, Jérôme. How are you?
Another way of proving the existence of the limit value is by a characterization in the literature. We have the Mertens system of solution. With Rida, we have a paper showing and characterizing the existence of the limit value for product stochastic games, which are irreducible. And Rida also has a formula for the value of absorbing games, the limit value. So here, can you think of a method to a characterization of this in this spirit of a Mertens solution combining with Rida's formula for absorbing game, or something else related to Mikkel's approach to prove existence of the limit value in a standard stochastic game? This would be alternative options to try to do it, not with approximation, but trying directly to characterize the limit. Do you think it's possible? Or?
I think it's very interesting to characterize the limit, but here somehow I don't know how to do it, so that's why I'm using this approach. I mean, I think the advantage of this approach is that it kind of separates the problem of characterization and the problem of existence.
Have you tried the other approach? This is my question, more or less. Or you haven't?
I mean, I know the papers, but not so hard. Sorry. I mean, I know that. Yeah. No.
Jérôme, I claimed several years ago that I have a proof with this approach, and I think I have it, but I should write it. But which gives the characterization, but it says nothing about uniform value, like in this, you know. And I don't think.
No, but the point is that okay. Actually, my target was not really specifically absorbing games. So okay, of course, in absorbing games, you may get a characterization. But if you target, like for instance, stochastic games with incomplete information, the general model, where you have a collection of stochastic games and you just don't know which one you play, then characterization will be very difficult. I mean, it's only recently that we get some characterization of limit value by Mikkel's work, but then trying something even more complicated, maybe. So that's why I think what is efficient in this approach is that you kind of decompose your problem into several sub-problems that are easier. So you really target the existence, even if you want to be able to do it, to characterize it. So I think that this approach has also its virtues. And I would also like to investigate the problem of maybe discretizing the new universal belief space. I think there is also interesting things to do that. And you can see that typically if you get a complicated universal belief space, it will be very hard to have a
I couldn't hear you. You said
characterization.
I couldn't hear you. You say discretizing what?
The universal belief space.
Universal belief space. Okay.
Because it's compact, so maybe you can do something like this.
So here you think of the model of a repeat game with incomplete information on both sides, where you have signals depending on the state.
Exactly. Yeah, exactly. Yeah, and asymmetric. Yeah.
This model can be attacked this way, maybe.
Yeah. I mean, actually, that's my main goal is really to understand like when are the Mertens conjectures true, not to target specifically absorbing games.
Bruno, can you add signals to your models of absorbing?
I don't know.
Maybe you can.
Public signals, maybe. I don't know. But what do you mean signals about what, by the way? No, but the point is that in absorbing games, there is only one non-absorbing.
Yeah, public signals, yes. But if it's not, the space will be,
And if you want signals on actions, then you go to the universal belief space, and then I don't know. Typically, I don't know.
Okay, thank you.
So thank you all, and hopefully see you someday.
Thanks, bye.
Bye bye.
Bye. Thank you.
Bye bye.
Bravo. Bye.
Bye all. Bye.
Galit, can you cut the...
Bye bye. See you.